Hello, my name is Daniel Reynolds. Today I'm going to give a talk on high-order multirate time integration for multiphysics systems. This is joint work in collaboration with my PhD student Rujeko Chinomona and a collaborator Luan at Mississippi State University. So basic outline of the talk, I'm going to go over some background about multirate methods and the type of problems that we really investigate. Then I'm going to focus on three different papers that Luan and Rujeko and I are working on to kind of extend these background things that I'll discuss. And then I'm going to give some conclusions and discuss where I see future work in the area. So first, we really focus on what are called multiphysics problems. Multiphysics problems typically involve a variety of interacting physical processes. They might be systems of equations that are coupled together throughout a domain, say reactions and diffusions, or combustion, other kinds of things. Or they could be systems of components that are coupled across interfaces. So you could have some subset of the domain where one type of physics is dominant, another type of the subdomain of the domain where another type of physics is dominant, and they really couple together through an interface. And so multiphysics simulations can pose some challenges that a lot of other applications don't really have to deal with. So they can be multi-rate. Maybe one physical process really requires or demands a much smaller or larger time step size than another, but they aren't so much faster or slower that you could make some simplifying assumption that say something's in equilibrium or steady state or those kinds of things and kind of simplify the problem. You really need that the fast operates at a faster time step size, but they're coupled together. You could have optimal solvers for some pieces, but not everything altogether. And you can have a mixture of stiff and non-stiff processes that really pose a challenge for kind of standard fully explicit or fully implicit types of methods. So here we're going to consider the prototype problem y prime is equal to fs plus ff. Here y is a vector in Rn and can be very large for these large multiphysics types of applications. Fs is part of the right-hand side that contains all of the slow stuff, and it would really like to be evolved with a time step size of capital H. Meanwhile, ff contains all the fast components, and that would really like to be evolved with a time step size of little h. And so little h would be much smaller than big H, think 50, 100, 1,000 times smaller. Now, on top of that, you could further decompose the fast or slow portions of the right-hand side in implicit or explicit, or you could further multi-rate into other fast and slow components, etc. But we're just going to think about this prototypical problem for most of the talk today. So historically, people have been doing problems that are multi-rate for many decades. And these two kind of workhorse legacy algorithms I'm going to talk about have been in use since the 60s. And moreover, most everybody who I talk to who does a multiphysics type application on the physics side, they use one of these two things. They don't use any higher order, fancier stuff. They use these kinds of basic approaches. So let's kind of understand what we need to beat. So historically, people would use a first order operator splitting and subcycling to do a time step. And so just kind of to see the basic structure, you can imagine doing a slow step that's a forward Euler, where you go from yn to what, instead of yn plus 1, it'll just now be this intermediate solution yn 1. Now, that yn1 is the initial condition that you use for solving a fast ODE with the fast right-hand side. And so you define this fast ODE, just the fast right-hand side. And then you evolve from that initial condition based on the result of your slow over the full time step to get to your new solution. And so you kind of couple these together through initial conditions is one way to think about it. Gil Strang and also, I don't remember his first name, but Marchuk back in the 60s came up with a different approach that is more accurate than the basic first order approach. And the basic idea is you symmetrize what you're doing. And so you can imagine doing your slow half of a step at the beginning, solve the fast problem for the whole time step, and then half of a slow step at the end. Now here, if you want the overall method to be higher order, you need each piece to be higher order. And so this is a second order Hoyne at the front, outside of the sandwich. And on the inside, we're doing this fast time scale. And I'll note that you can order these in different ways. You could have the half of the fast time scale first, and then do the full step with the slow, and half of the fast, etc. And when you have really complicated multiphysics applications, there's kind of an art form in how one does the layering of fast and slower, etc., to kind of build these things all together. So unfortunately, these approaches, although they're really flexible, can suffer. So they're typically really low accuracy. So that first order splitting is first order. Strang splitting is even only first order unless the operators commute and you do it appropriately. And so on top of that, you could do some kind of extrapolation process, but that can become relatively costly rather quickly. And so just to kind of see, Ropp and Shadid a number of years ago did a study of operator splitting methods. And first order operator splitting is right here, this solid line. And the Strang type of approach eventually is second order for very small step sizes, but for a while, it had no convergence at all until you get to a small enough step size, and then it jumps down. And so that I've seen that in other applications as well. It's kind of weird inaccuracies for straying, that sort of thing. S-stepping collaborators have also shown that these type of subcycling things can have some poor stability properties. So even maybe each part uses a stable step size for its own piece, say they satisfy their CFL condition at each time scale. When you put them together, because they're actually coupled and you're pretending they're not, you can have some unstable modes. And so here, S-stepping collaborators are just looking at reaction diffusion. And if you had even 10 subcycling reaction steps per diffusion step, you could move your part rather significantly from the smooth solution manifold that you normally have. And that could give rise to some severe instabilities. So in recent decades, people have been making better methods, of course. And so I see these as coming in two basic flavors. So the first group thinks about coupling the two timescales more tightly than just through, say, initial conditions. And these typically require only a single traversal at a time step, maybe a couple traversals at a time step, but they couple things together more tightly in that traversal at a time step. And these are typically going to be second or third order accurate, at least up until the last couple of years. Alternatively, you can use some sort of extrapolation or deferred correction type technique, where you're going to traverse that time step over and over and over again. The base method might be that first order operator splitting the subcycle we mentioned earlier, but you're going to do that time step repeatedly as you bootstrap up to higher and higher orders of accuracy. And so this has a real potential for very high accuracy methods, but it's going to cost you to get there. So I know I have a bunch of references at the bottom. This isn't an exhaustive list, but all of these are hyperlinked. So if you download the slides, you can follow them to find papers where people do one of these various approaches. So there's a lot of areas potentially for improvement. We're going to focus in two ways. First, we're going to consider only methods that require a small number of traversals of each step. So we don't want to do a deferred correction type of thing. We want to be able to get that time step as efficiently as possible. We're essentially going to follow the tight coupling approach in order to essentially try to get something that's more efficient overall without really having to do something very costly. We're also only going to consider methods that allow freedom in how the fast time scale is integrated. Meaning, like that operator split and the straying thing before, the fast time scale just solves an ODE. So we're not saying how that ODE is solved, just that it is solved, and maybe that it's solved with a method of at least second or third order method. And so I'll note these two criteria seem to be at odds. A number of higher order tightly coupled approaches really dictate both fast and slow methods, so they can interleave operations to do interpolation between them, et cetera. And so we're going to try to focus on methods that don't have a battle between these two basic approaches. And so a starting point will be these things called multi-rate infinitesimal step methods. They've been around for a little while now, and they arose in the numerical weather prediction community. And this generic infrastructure really supports second or third order accurate methods for multi-rate problems. So this same kind of prototypical form I mentioned earlier. We think about the slow timescale as being integrated using an explicit outer Runge-Kutta method. And so that'll have butcher tableau ABC. And we have some stipulations that those abscissa, because it's explicit, the first C is equal to 0. They're sorted, and that the last one is less than or equal to 1. And so where they get their name infinitesimal from is the kind of theory underneath them assumes that the fast time scale is solved exactly, but instead of it being just the fast right-hand side, now it's a modified ODE for the fast time scale. So that's kind of where the coupling is going to come from. In practice, that fast thing is really just a subcycled inner Runge-Kutta method. So what does a step look like? We're going to have S stages. So the first stage, being explicit, is the old time step solution. For each internal stage, we define this forcing term R, and it's going to be a linear combination of the slow right-hand side evaluated at preceding stages. And so we're only going to take stages we've already computed. This linear combination we can compute just when we start each stage, and it's just some vector of size n that is going to be this forcing term, and it fits right here. So when we solve this fast initial value problem, it's not just what we had before, which was just v prime of theta equals f fast. Now it's v prime of theta equals f fast plus this forcing term. And so that really helps increase the coupling from the slow scale to the fast time scale. You solve these fast initial value problems over these little bursts over each little stage ci minus 1 times h to ci times h. And so since the c's are sorted, the sum of each of these, the union, I guess, of each of these intervals is the full time step. At the end of each of these fast bursts, the result of that is how you get your new stage solution. You loop over all of these, and your updated time step size is the last one you got. These alpha ij coefficients are uniquely defined from the slow butcher table, so the a's and the b's that you started out with. When two c's are equal to one another, notice that this time interval shrinks to 0, and this fast ODE evolution really just corresponds to a standard undercut update. And in reality, you can solve this fast problem however you like, any method you really want to use. So these MIS methods satisfy a number of desirable properties that we've been hoping for. So it's at least second order accurate, as long as both the inner and outer methods are at least second order. It's third order accurate if you use third order based methods, and that outer table satisfies this one algebraic condition. So we can get higher order. We need a little bit more about that butcher table we start out with. That inner method, some folks use it as being the outer method itself, and that allows you to telescope this thing. So you can have different layers of multirating going as far down as you'd like just by recursing the approach down. It's pretty flexible. You could use strong stability preserving at whatever kinds of butcher tables you want for the fast or slow, kind of to match the physics you're solving. And from a lot of tests that I have multiple grad students working on over the years, it's been very hard to find any method that really beats these MIS methods at third order or lower. And so they're really quite efficient because they require one traversal of that time. So very recently, in the last couple of years, a number of groups have seen the promise of MIS methods and extended them to higher order. So the first published one is by Adrian Sandu, his MRI GARC approach. And there he modifies the fast initial value problem. Instead of being just a constant vector, it's now going to be a polynomial in time. The fast time variable is theta. And so you again have this linear combination of old slow right-hand sides, but now the coefficients are polynomials of theta and not just numbers. And as a result, you get this polynomial in time that helps force the fast time scale. And so he's been able to use these to create fourth order accurate multirate methods, and as well as methods that are implicit at the slow time scale. And by implicit, this is called solve decoupled implicit, in that at any given slow stage, you either solve the nonlinear problem for the new slow stage in a Dirk type solve, or you do a fast evolution, but you don't mix them together into the same stage. Bauer and Noth this year have published a thing called this method they call extended MIS. It's quite new. It doesn't have a volume or anything yet. It's just the corrected proofs that are available online. And the basic idea with their approach is that Noth was one of the inventors of MIS, and what they've done is relax kind of what MIS looks like a little bit, and then from that they develop order conditions on that outer table, just like above, to guarantee higher order. And so now with this extended MIS approach, if that outer table satisfies one algebraic condition, you get third order. If it satisfies a number of algebraic conditions, you get fourth order, etc. A previous grad student of mine, Jean Sexton, has what she called a relaxed multirate infinitesimal step method that instead of getting the new solution as the result of a fast initial value problem at the end, you do all the fast initial value problems for each internal stage, and then you build up your final solution as the full right-hand side evaluated all those internal stages. And what she was able to get is a fourth order accurate overall method that conserves linear invariance as well. So the focus of this talk are on these new methods that we've been working on in the last couple of years. So the first I want to talk about are these methods called multirate exponential Runge-Kutta methods. The paper just came out, I think in January in CISC, where we introduced these and showed a bunch of results. And so I'll kind of summarize that in the next few slides. So we're going to consider a class of multirate problems where we have a fast time scale that's linear. So it's all encoded in this matrix A, and G is all the slow stuff. So all the nonlinearity has to be at the slow time scale for this type of method, just as a caveat. I'll note this problem structure is the exact same structure as assumed by exponential Runge-Kutta methods. And so if you're familiar with exponential Runge-Kutta methods, you can frequently write them in the following form. There's internal stages. I use stage Z type stuff because that's what we've been using already. In general, exponential methods folks don't use Z for that, but that's okay. Each stage is written as essentially the old time step solution, this phi function, a matrix function evaluated at CIHA, times your full right-hand side. And then you have a linear combination of these other matrix coefficient functions Aij times these DNJs. And the DNJs are really just G evaluated at the stage minus G evaluated at the time step. So think of, when you see D, think of the Gs essentially. And so you get these internal stages like you have with a regular Runge-Kutta method, but now there are these phi functions, these matrix functions that you have to evaluate. And these coefficients Aij and Bi are really just linear combinations of more and more phi functions. And so in order to use an exponential method, you have to be able to evaluate those phi functions accurately and efficiently. And so what Luan really figured out was that if you take one of these exponential Runge-Kutta methods, and if it satisfies the following assumption that these these coefficients ai, j, and bi are strict linear combinations of these 5 functions evaluated as ci, ha, and ha respectively, so this specific format here, then those internal stages and the updated time step solution are actually the exact solutions of these modified fast initial value problems. And so the internal stages are the solution of this fast ODE, this fast ODE at the time CIH. And the updated solution, once you've gotten all those internal stages, is you evolve this fast ODE again, and now you're going to get the solution for that at H, and that will be your updated time step solution yn plus 1. So this feels a lot like MIS. Now, these fast ODEs, remember the fast operator was A times the unknown. So we still have the fast operators here, and these modifications are polynomials in time. So here these D's are really just the slow G's, remember? Here's another G. So it's really a linear combination of the slow operator, where the coefficients come in this form here, where they're really essentially going to be polynomials in time again. So it feels similar to Adrian Sandhu's MRI-GARG approach. So assuming that a Merck method is constructed from an exponential Runge-Kutta method that has order P, and you solve these fast problems for the internal stages with methods of orders Q and R respectively, and if the fast and slow time step sizes relate by a factor of n, then the global order of the method, we were able to prove satisfies this bound here. And so we see that the overall method is bounded by h to the p. That comes from the exponential Runge-Kutta method. It's bounded by little h to the r. That comes from the fast method for solving the overall time step. And the internal stages, this error comes is essentially big H times little h to the q. So we solve each internal stage with a method of order q, and we gain an extra order from there. So what that really kind of says is you could use a fast integrator for the internal stages that's 1 order accuracy lower than the other guys if you wanted to get an overall method of order 3 or 4. Now I'll note that these ODEs are always solved over the interval 0 to CIH. So meaning that the overall reversal time for that time step is 1 plus the sum of the C's times H, which is larger than just 1 times H typically. Now it's usually not any bigger than 3H. So thinking of MIS, we'd go over that time interval once, and MRI-GARG would go over that time interval once. Well, now we can go over it a few times, but not that many. So here are some results from that paper. We can see that there's these 2 test problems that I'm highlighting here, this bidirectional coupling test problem and this stiff bruslator test problem. And the main takeaway features here are that we obtained the expected orders of accuracy 3, 4, and 5. We can compare them against some of Adrian's MRI-GARG methods of order 3 and 4, and we get the right orders of convergence. We have a pretty good comparison as far as the error constant is, smaller than those MRI-GARG methods, at least for this test problem. Here they're closer, but these new methods are still a little more accurate per step than these MRI-GARG methods. And I'll also note we have a 5th order method, which I've never seen before. On top of that, we have some new work that we're working on right now. We probably will submit this a little later in the fall. We're calling the Multirate exponential Rosenbrock. And so here we again think of an overall initial value problem that has a similar structure as before. So this last one, remember, we had AY as the fast operator, and then the rest of it was in this nonlinear thing G. And so now we have JY as the fast operator, and then the rest of it is in blue. And specifically, unlike the Merck, where it could be any linear operator you wanted here, J must be the full Jacobian of f with respect to y, the full right-hand side with respect to y. And similarly, this V will be the full derivative of f with respect to t, meaning that the gradient of n, the partials of n with respect to t and y at Tn is going to be identically 0, because n is the leftovers after you subtract off the linearization terms from f. So if the problem has this basic structure, we'll point out that this is the same structure as assumed by exponential Rosenbrock methods. And so exponential Rosenbrock methods look similar per time step to exponential Runge-Kutta. But because they have some structure, you know, that this is the full linearization with respect to y, that this guy has partial derivatives that are equal to 0 at t and yn, the order conditions are simplified dramatically. And as a result, you can have much higher order accurate exponential Rosenbrock methods than exponential Runge-Kutta methods for the same number of stages. And so we've constructed MERB methods of orders 2 through 6. So these are the first ever 6-order accurate, tightly coupled multivariate methods. And even MERB 6 only has a traversal time of essentially 1 1/4 the width of the time interval. So it's not much more than 1 traversal of the time step. So these results are fresh off the presses. Essentially for this, another bidirectional coupling test problem that is tightly coupled from the fast to the slow and the slow to the fast. We see kind of superconvergence that we don't understand yet. The MERB 3 and the MERB 5 methods are orders 4 and 6 respectively, whereas the MERB 4 and the MERB 6 are just orders 4 and 6 like expected. So we don't understand that yet. We're still trying to investigate. And there, so far we still need to compare them against other methods, et cetera, but they seem to be rather efficient, and that 6-order method is really hard to beat as far as the MERBs are concerned. Another test problem is a reaction diffusion test problem, and this one shows the expected rates of convergence 3, 4, 5, and 6 as we do these problems. And again, these are really new. So if you have questions, we can talk about them, but we're still investigating this kind of stuff. So the last methods I want to talk about are these implicit explicit multirate infinitesimal step methods, and these are part of Rujeko's thesis work. We're about to submit this probably in the next week or two. And so here the idea is we're going to take the slow operator and split it into implicit and explicit parts. And so other than that, it's essentially the same as what Adrian Sandu's MRI-GART method does. We have a forcing term that's a polynomial in time. It will be these coefficients are polynomials in time, and they're linear combinations of the Fi now and Fe. So it feels very similar to Adrian's methods. We provide order conditions for the gammas and omegas up to 4th order, and they really rely on the GART framework that Adrian and Michael Winter had in 2015. I don't really have time to go into how we build them, other than to say we start with a base additive Runge-Kutta method. So a standard additive Runge-Kutta method where we're assuming internal consistency so that they share the C's, and where those C's satisfy those same assumptions that MIS had. And on top of that, we have, then we derive the gammas and the omegas to satisfy a bunch of stuff. I can come back to this if anybody has questions. And so we've developed 3 methods, IMEX MRI 3A, 3B, and 4. The IMEX MRI 4 method, it doesn't have the stability we'd like right now, so it's not really, I'm not proposing it for general use, but we are going to use it for some convergence test results in the next slide. But the 3A and the 3B, the 3A just satisfies the order conditions, and the 3B, we've really done some rigor, some optimization to try to make that as stable as possible. And so looking at joint stability, here's a 3A method and here's a 3B method. And what we can really see are that these curves, again, we can talk about joint stability a little bit later if anybody has questions, but for a wide variety of angles for the fast and implicit, so for the fast and the implicit time steps, we get kind of smaller stability regions here for the unoptimized and much larger stability regions here for the optimized versions. And so we really like the 3B method. As far as convergence is concerned, on the nonlinear Cavero-Prothero-Robinson test problem, this is one that Adrian uses a lot for his tests. We can measure convergence rates that are exactly what we'd expect, about 3 and 4. The first order operator splitting and the string splitting both show essentially first order, and we think that's just because the operators don't commute. Over here we have a stiff brushlator test problem, kind of the same one that we've seen in a number of previous slides. Here, string eventually gets second order after some initial floundering around. Our new IMEX MRI methods do what they're supposed to do. Everybody has a slight amount of order reduction. And we note that this 4th order method, we don't have any dots to the left of here because it's not as stable as we'd like, but it's fine for estimating convergence. So just to conclude, although they're pervasive in multiphysics computations, those simplistic operator splitting and subcycling approaches really remain the norm. And what we really want to do is come up with new, flexible, robust, better methods that can break their monopoly. So I've kind of taken the liberty to categorize a bunch of this stuff, but let's say you have a problem that allows explicit treatment of a slow time scale. Well, if you want a 3rd order accurate method, there's a bunch of choices out there. A 4th order accurate method, there's a bunch of choices as well. If you need 5th or 6th order, you need MERG or MERB, and both of those either require that the fast time scale is linear itself, or that it can be approximated by a linear operator. That's pretty good. If you need implicit treatment of the slow time scale, there are MIS methods that can do that, or MRI-GART methods of orders 3 and 4 that can be used. And if you want IMEX treatment of the slow time scale, then these new methods that Rujeko is coming up with, these IMEX MRI methods, really allow 3rd or 4th order treatment of the overall multivariate problem with IMEX treatment of the slow time scale. nearly all of these methods allow nearly arbitrary treatment of what goes on at the fast time scale. You define fast modified initial value problems and you solve them however you want. And so those fast time scales could be implicit, explicit IMEX, or even multi-rate again. And so you could do all kinds of things with this flexibility, should you choose to do so. And I'll note that almost all the methods I've talked about really can be extended to allow for temporal adaptivity of both the slow and fast time step sizes. So a lot of work remains to be done. If you want to do a time adaptivity, how do you come up with a robust time adaptivity controller when you have multiple knobs to turn? So maybe fast and slow, or even if you have a bunch of multi-rating you layer on top of one another. How do you pick these time steps to get accuracy that you need with as little work as possible? We're really interested in advanced algorithms for solve-coupled MRI GARC and IMEX MRI. So that's where you have a slow stage that both requires a nonlinear implicit solve for that stage, but it's also involved in the fast timescale evolution. So you have a nonlinear problem that requires you to evolve the fast timescale for every evaluation. So that's going to be costly. And so some advanced algorithms for solving that implicit problem would be nice. We'd really like some rigorous stability theory for additively participant ODE systems. All of this joint stability stuff that I've shown you really uses this kind of simple modification of the Dahlquist test problem. And that really assumes simultaneous diagonalizability of the problem, which is essentially never true for multiphysics applications. So although it's nice to know how stable we would be for such a simple problem, it's hard to use that problem to predict performance for just generic applications. We're working on new gamma K and omega K tables for fourth order accurate IMEX MRI methods. It would be nice if there was also theory for fifth order and sixth order accurate MRI GARC and IMEX MRI methods. And lastly, to really get this stuff in use, it needs to be implemented in high quality, robust, and efficient software. And so, and I'll note that we're working on that kind of stuff as well, so that multiphysics practitioners will actually use these kinds of new methods in their work. So with that, I'd like to thank you for your time, point out collaborators and students and grant and computing support, and I'd be happy to answer any questions you might have. Thanks.